about exponential growth today, and specifically the exponential growth model. Now, something's growing exponentially when it's going up by the same percent each period of time. And so typically the time period that we'll be working with for this section here are in years, and so a lot of times T will represent years for what we're doing. R is the rate of change, and so that'll be that percent that it's increasing each unit of time there. Remember that when we work with percents in math problems, we want to change those to decimal form. So you'll be seeing me do that as I go through some problems here. Now notice that 1 plus r is in parentheses there. The 1 plus r is actually that growth factor. That's really what's going to determine how much it's going to grow, is that 1 plus r. And so the bigger that r is, the higher the percent that is, the more that we're going to see that exponential growth. Now, with everything, there's a starting point there. And so C is that kind of that initial amount that we're starting with. No matter what the situation is, there's some initial amount that we're going to begin with. And then as it grows from there, that's where it starts, the initial amount. And so, looking at our first problem here. A savings certificate of $1,000 pays 6.5% annual interest compounded yearly. So the nice thing is when you put money into these savings certificates, they'll actually give you money over the course of time there, and they're worth more when you cash them in. It's asking here, it wants to know what the balance of the certificate is going to be after 5 years. When it says matures there, it just means that it stops growing after 5 years. So this won't grow forever. Eventually it'll stop growing. It won't be worth anymore. So let's go ahead, let's work this problem out here. It says the savings certificate is worth $1,000. So that's going to be that initial amount. That's how much it's worth right away. If I don't do anything else, I still have $1,000. It's going to go up 6.5% yearly. And so the 6.5%, I want to work with that as a decimal. So remember, you move it 2 spots, 1, 2, so it's going to be 0.065. And then the t, the exponent that I'm taking it to, that's the number of years that I'm looking at. And in this particular problem, I'm looking at 5 years. And so now I go ahead and do my math. Follow those order of operations. 1 plus 0.065 is going to be 1.065, parentheses first. Now do your exponents. When you go ahead and you can use calculators here, so go ahead and put 1.065 to the 5th power on the calculator. You might be surprised when you do that. When you do that, you get 1.3700866, and it goes for a while, but I want to try to get as accurate as I can. So you kind of got to look at this number to see how far you want to go. I chose that many digits on my calculator for a reason. I think you'll see it now. When I multiply by 1,000 here, I'm going to move it 3 places. So 1, 2, 3. So it's going to be $1,370. We're talking money here, and so the reason why I chose this many decimal places is I knew when I moved it this far, I still needed to have a couple places for knowing the amount of cents I was going to have there. And so since this is a 6 here, that's going to bump that up to a 9. And so I'm going to get back, after 5 years, $1,370.09. Now we'll come back to this problem specifically. We'll come back to the model here that we have at the beginning. But let's take a quick look at one more problem, now that you kind of hopefully get it there. This is an experiment with bacteria, and a lot of times bacteria will grow very rapidly and exponentially a lot of times. So it goes up by a certain percent each unit of time there. This time we're going to be working with the time being every hour. So an experiment started with 100 bacteria, and then they're going to double in every hour. This will create some difficulty in a sense that they didn't actually give us the percent. They didn't just flat say it's going up 20% or it's going up 30%. They said it doubles though, and so we'll have to really work with that. It wants us to write the model for the number of bacteria after 8 hours. So remember, our time that we're working with is hours, so we're going to be okay with that. The initial amount is 100. I know I'm going to have 1 plus that rate, and I know it's going to be every hour for 8 hours. So this is the kind of easy stuff to get plugged in there. This is the one I have to think about, is that rate of growth that we're going to have there. It's doubling, and when something's doubling, I mean it's going up 100% of what you had before. So since it's going up 100% from what I had before, that means it's going to go up 1. So it's going up 100% every hour. To turn that into a decimal, I move it over 2 places to the left. That is 1. Now 1 plus 1 is going to simplify down to be 2. And so really when I go to find the number of bacteria after 8 hours, what I'm going to do is I'm going to take 2 to the 8th power, and then I'm going to simplify that down there. So 2 to the 8th power actually turns out to be 256. When I multiply that, I get 25,600. And so after 8 hours, there are going to be 25,600 bacteria.